So before talking about implicit differentiation, I think it's important for us to talk about the power rule. If I have x to the n, and I take d dx of x to the n, that is just equal to n times x to the n minus 1. An example of that could be y is equal to x to the 4th. So the derivative of y is equal to 4x to the 3rd. The other notation that I use is I say I take d dx of both of those, and that will give me dy, the derivative of y with respect to x, is equal to 4x to the 3rd. So notice that what I have here is that y prime and dy dx, those are the same things. Now, what if I had y to the n power, but I wanted to take the derivative with respect to n? You already saw the derivative of y with respect to x is equal to dy dx. But now this is not just y anymore, it's y to the nth power. So the idea of doing this is exactly the same. This is just equal to dy dx, the derivative of y with respect to x, the derivative of my variable y with respect to x. Now I take the derivative of y, which is n times y to the n minus 1. And what this allows us to do is have a single unified derivative. So this is really helpful when we have equations like circles. X squared plus y squared is equal to 25. To find the derivative of this, the notation that I'm using is I want to take the derivative with respect to x of all of those parts of this function. This equation. The derivative with respect to x of x squared is just 2x. The derivative with respect to x of y squared, because these two don't match up, I need to put in there, this is now the derivative of y, my new variable, with respect to x. Now I go through and take the derivative of y, which again in this case is just 2y, and the derivative of 5 is just 0. So solving for dy, I have this as I take the 2x, I subtract it from both sides, moving it over here, leaving me with dy dx of 2y is equal to negative 2x. Divide both by 2y, and I'm left with dy dx is equal to negative x over y. Now let's take a look at what this is. This first graph was a circle, correct? And the circle had a radius of 5. Now, what does that mean? It means that if any point I want to go ahead and find at 2, I can find the slope of this tangent line. What would the slope of this tangent line? Well, first I have to go back to my function being x squared plus y squared is equal to 25. And since I want that value at 2, the first thing I have to do is find the point. What is this point here? I need both the x and y value. So 2 squared plus y squared is equal to 25. Y squared is equal to, I subtract 4 from both sides and get 21. So y is equal to technically plus or minus the square root of 21. That gives us a point here at 2 square root of 21, and also down here at 2 negative the square root of 21. But I'm interested in finding the equation of this line at that point to positive in the first quadrant for this question. So what that means is if I go back to my dy dx, my negative x over y, that tells me my slope at this particular point is going to equal negative 2 over the square root of 21, or 2 square root of 21 over 21, and that does need to be a negative. Now, let's say I wanted to go through and find the slope of this line down here. The point on this graph, as I said before, is 2 negative square root of 21. So to find the slope of the line that I have in yellow, I still plug it back into dy dx. Remember, this is the derivative. The derivative gives us an equation that will yield the slope of the tangent line at a given point. It is in terms of both x and y because I need it to be in terms of both x and y because that is this point here. Plugging that in will give us negative of 2 over negative 21, which in this case, when I rationalize it, will give me a positive 2 square root of 21 over the square root of 21.